Welcome to the Quantum Gravity channel.
For nearly a century, the ultimate prize in physics has been a single framework that explains both the sweeping curves of galaxies and the microscopic jitter of atoms. We call this theoretical holy grail quantum gravity. What you might not know is that physicists already have a mathematically complete equation that tries to do exactly this. It's known as higher derivative gravity, and it looks like this: r plus r squared plus c squared. But writing an equation is only the first step. For any quantum field theory to be valid, it has to stand on three strict mathematical pillars: locality, renormalizability, and unitarity. This specific higher derivative equation performs beautifully on the first two. It easily satisfies locality, meaning cause and effect behave normally in space, and renormalizability, meaning the math doesn't spin out into infinite, unsolvable nonsense. The problem is that third pillar. When you run the numbers for higher derivative gravity, unitarity completely collapses. Unitarity is a basic bookkeeping rule of reality. It states that if you add up the probabilities of every possible outcome of a quantum event, the total must equal exactly 100%. If a theory breaks that rule, you end up with outcomes that have a negative 20% chance of happening. A universe with those rules is logically impossible. Because of this fatal flaw, standard perturbative quantum gravity was largely abandoned for decades. The specific mathematical anomaly that breaks unitarity in this equation has a name. Physicists call it a ghost particle. A ghost is a mathematical consequence of the equation that carries negative kinetic energy. When these ghosts interact, they cause the probabilities of physical events to wildly exceed 100%, or drop below zero. This is a photograph of Richard Feynman. His famous diagrams are the standard tool physicists use to chart out how normal particles interact. When you use standard diagram rules to map out higher derivative gravity, ghost particles inevitably appear inside the loops of the math, creating highly unstable, mathematically impossible feedback loops. Because these ghosts destroy the predictive fabric of the math, the physics community mostly turned away from this equation, migrating toward highly complex, difficult-to-test alternatives like string theory to bypass the problem entirely. But recently, a new approach has emerged. What if the equation itself is perfectly fine, and the error lies in how we quantize it? This brings us to a new mathematical classification called the Fasichon, or purely virtual particle. Unlike normal virtual particles that briefly pop in and out of existence, a Fasichon is mathematically projected out of the physical spectrum completely. It mediates interactions that it can never become real and will never trigger a physical detector. Using Fasichons to neutralize the ghost problem requires a radical trade-off. To make the math work, physicists must intentionally violate what is known as time ordering. This violation happens at an unimaginably small scale. At distances smaller than 10 to the 13 giga-electron-volts, negative, the strict sequence of cause and effect becomes fuzzy. The sequence scrambles, allowing events to briefly bleed into the past. By accepting this microscopic violation of time ordering, we permanently cage the ghost. The result is a unique, perturbative quantum gravity theory that is completely renormalizable and perfectly unitary. Theoretical consistency is only half the battle. To verify the math, we have to look toward the massive canvas of the observable universe. Unlike many other quantum gravity proposals, the Fasichon model makes strict, observable predictions about cosmic inflation, the rapid expansion of the early universe. This image shows the cosmic microwave background, or CMB. It is a map of the oldest light in the universe, where primordial quantum fluctuations were permanently frozen in time. Within this radiation, physicists look for a specific observable metric known as the tensor-to-scalar ratio, represented by the letter R, which measures the footprint of primordial gravitational waves. This diagram illustrates the exact narrow numerical window the Fasichon theory demands. It predicts a tensor ratio strictly between 0.0004 and 0.0035, tied to a relationship where r equals -8 times the tensor tilt. This is a photograph of the Planck satellite in a clean room, representing the highly advanced observatories currently deployed to search for this exact signal. If upcoming observations detect a tensor ratio within that precise mathematical window, the Fasichon prescription will have physical proof. It will move from a theoretical correction of time to the proven rule of our reality.